once again. So hello everyone and welcome to another ICTS virtual string seminar. Today we are happy to have Stephane from Brussels University with us, and he's going to talk to us about the 3D black string and its dual. So over to you, Stephane.
Okay, so hi everyone. I hope you're doing well. And so first I want to thank you for the invitation to give this this talk here. It's my first talk in India, as I was telling Vishal. So it's a real pleasure to be here and to tell you about this paper that came out so a year and a half ago, and that was written with Louis Apolo and Wei Song, that I thank here for a really nice collaboration. So okay, so this is the schematic plan of today's roadmap. So okay, so don't be scared about all the bubbles and squared and everything. So because we will go through all these corners of this diagram in the course of the talk. So I want to say those, so don't hesitate to interrupt if you have questions. And okay, so let's begin, and we'll take this diagram here. And we will start by this corner here on the bottom left. So in August 91, Horne and Horowitz posted a paper on the archive, and that was called Exact Black String Solutions in 3 Dimensions. So this was almost 30 years ago, and this was actually the first paper to ever appear on the archive. So Gary Horowitz is telling the story, and he's really proud of this. So so what is this solution? So what did this paper contain? So in that paper, the authors introduced charged black string solutions in 3 dimensions. And that had the interesting property that they were described by exact conformal field theory and an exact target space conformal field theory in terms of a gauged West-Zumino-Witten model. Okay, so here below I have put the background fields. So that's a solution of 2B string theory compactified to 3 dimensions. And so in this solution, what we have, so we have the mass here of the black string. We have the charge of the black string. And we have here K, that's the effective cosmological constant related to the ADS length. Okay, so so this is the background. And what was interesting about this solution is that it provided a simple exact CFT description of a background in 3 dimensions that was qualitatively really similar to the Reissner-Nordstrom black hole, to the charged black hole in 4 dimensions. So to see this, well, Horne and Horowitz, they did draw a Penrose diagram of that solution, and what they found was the following. So this diagram is actually familiar from the Penrose diagram of the Reissner-Nordstrom black hole. So we see that we have an outer horizon at r equals r plus, that's given by m. We have an inner horizon at r equals r minus, that's given by q squared over m. So here we have a time lag singularity that's actually a curvature singularity. So we have a singularity at r equals 0. Then we observe, we can see that this solution is in some sense asymptotically flat. So we see this here at the asymptotic structure when drawing the Penrose diagram. And this can be seen also on the scalar curvature that goes to 0 as rho goes to infinity. So interestingly, that solution also has, it's of course, it's a thermal solution. It's a black hole, black string solution. So it has a Hawking temperature that is given in terms of the charges by 1 over pi m squared minus q squared over 2k. And also really interestingly, of course, it has a Bekenstein-Hawking entropy. So here, if it's a string, or if it's a string, is the entropy per unit length, or you can compactify the string length, and you get the Bekenstein-Hawking entropy that is given by 1 over 4 GL. That's given by m squared minus q squared over square root of m squared minus q squared. So of course, this begs the question, well, is there a microscopic understanding of this black string? So this is a question. So microscopic understanding is, can we count? Is there a microstate counting of the black string that reproduces the macroscopic RELO? So this is actually a question that, well, could have been asked in 91 when the paper came out. But well, for some reason, well, no definite progress actually was made in this question. So explaining the microscopic entropy of the three-dimensional black string. And actually one reason for this is that 1 year later, so in 92, there's another solution that appeared on the market. And this solution is the familiar BTZ black hole that is asymptotically ADS3. So, and of course, this BTZ black hole played a central role in, well, an increasingly central role in the newly discovered ADS-CFT correspondence that appeared 5 years later. So here, if you compare the number of citations to the black string paper to that of the BTZ paper, you see that there's about 10 times more citations to BTZ than to the black string. Okay, so the goal of this paper will be to try to find a microscopic description of the three-dimensional black string. But to do so, what I will do, I will start by reviewing what is known and what we can do in ADS-CFT. So I will keep our goal in mind, which is to describe the 3D black string. But however, I will try to use the tools that we have gathered from ADS-CFT for more than 20 years now, so almost 25 years. So ADS-CFT, of course, it's a really dense subject, and there are actually many open questions and recent developments. So of course, I won't be able to review everything. So what I will do here, I will just focus on the bits and pieces of ADS-CFT that will be of direct relevance to us. So that will be the first part of the talk. Okay, so what is the BTZ black hole? So the BTZ black hole is described by this metric here. So R plus and R minus are just the locations of the outer and inner horizon. So coordinates are TR5, phi is compact. And the ADS radius is related to the cosmological constant by this relation here. So that's one coordinate system that is used for BTZ. If you're familiar with BTZ, you have seen this metric a million times. But we'll also use another coordinate system for the BTZ metric, that's just this new U, V, and R coordinates, in which the metric is expressed not in terms of the inner and outer horizons, but in terms of the left and right temperatures. And U, V are related to the original phi and T of ADS by this relation here. So what is really interesting actually about 3D gravity is that about the BTZ black hole is that they are asymptotically ADS3. So at large radius, they behave like ADS3. So asymptotically ADS3 spaces were studied by Braun and Hainaut in '86. And it was shown that the phase space of asymptotically ADS3 spaces is endowed with conformal symmetry. That means that the boundary conditions at infinity are preserved by conformal transformation. So with conformal symmetry in 2D, they're generated can you, because I realize it's, okay. I hope you can read. So the phase space is endowed with conformal symmetry that is generated by the, let's say, the Virasoro vector fields given by this, and where x plus minus are, well, other light cone coordinates related to 2t. Well, they're almost similar to u and v, but up to a sign. So the phase space of 3D gravity is endowed with conformal symmetry. And now the corresponding charges defined as conserved, asymptotically conserved charges associated with this Ln plus satisfy a Virasoro algebra. So let me write this a bit better. With a non-vanishing central charge that is given in terms of the ADS radius and three-dimensional Newton's constant by this relation here. And this was shown at Horne and Horowitz. Okay, so this actually suggests a close relation between, quantum gravity in ADS3 and a two-dimensional conformal field theory. Because if the classical phase space is endowed with a symmetry, well, you expect that upon quantization, states will form a representation of that symmetry and a representation of the Virasoro algebra. Well, a theory where the Hilbert space is a representation of the conformal group is just a two-dimensional conformal field theory. So this suggestion that was based on the result of Braun and Hainaut was actually reinforced when it was observed that the entropy, so the Bekenstein-Hawking entropy of the BTZ black hole, which is just the area over 4G, that's given by, so 2 pi r plus over 4G, is actually reproduced by the Cardy formula. Where E left and E right are just the zero modes of the Virasoro charges and are related to the mass and angular momentum of the black hole through this relation here. So actually, this seems to indicate that the entropy of the BTZ black hole is found to match that of a hot fluid of strongly interacting particles in a two-dimensional conformal field theory. So this matching is due to Strominger and was done in '97. So that's a really interesting result. And actually, it has drawback. I mean, so the Cardy formula is a really universal formula that applies to any CFT that satisfies certain conditions, such as unitarity or modular invariance. So to apply this formula, we didn't need to know what the details of the underlying CFT are. So that's a strength. But on the other hand, this matching actually doesn't tell us much on what the 2D CFT, what the exact 2D CFT actually is. And this is still an ongoing question in some setups like pure gravity or even in string theory to identify the precise two-dimensional CFT dual to a three-dimensional ADS3 background. However, there is one thing that this formula is telling us, because we know that the Cardy regime in which the Cardy formula applies typically is when the temperatures are really high or the energies are really high. However, this formula, I mean, it has an extended range of validity that is actually called the holographic regime. Holographic regime would be, well, large central charge. So the length of the horizon, for example, is much bigger than the Planck length, or the ADS radius is much bigger than the Planck length. Gravity is classical. But however, this formula applies also when the left and right central energies are of the order of C. And actually, it's not every CFT will have an asymptotic growth of states that satisfies the Cardy formula here in this regime, in this holographic regime. So CFTs satisfying this condition will be called holographic CFTs, and Hartmann-Keller and Stoica showed that the condition for the growth of state to be given by this in this regime is that the spectrum should be sparse. So there shouldn't be too many light states.
C is much larger than what?
So C has no dimensions, so it's dimensionless.
Oh.
So C typically would be L over G, the ADS radius over the Planck length in 3 dimensions. So C counts the number of degrees of freedom, actually. So just, yeah, a number. Okay.
Okay.
Oops. That's it. I lost my slides. Okay. Okay, so this is so far in gravity. So there is actually one setup where we can try to go a little bit further and where we can try to identify the dual CFT in a bottom-up approach. And this is string theory. So string theory and ADS tree. So this is reviewed in this old but really nice review. So the Magoo review and the David Mandal-Wadia review of 2002. So the setup to explore ADS CFT in string theory is to consider type 2B compactified on a 4 torus, and considering a stack of D1 branes or F1 branes, and a stack of D5 branes and NS5 branes. So the 5 branes are wrapped around the torus, and they have an extra direction that they share with the D1 string. Now, one can take the decoupling limits of the system, so the low energy limit, to find the statement of the string ADS CFT correspondence, which is that type 2B string theory on ADS3 times S3 times T4. And depending on whether you have D1, D5, or F1 and S5, you will have different fluxes. So you will either have, in the D1, D5, you will have Ramon-Ramon fluxes, or in the case of the NS5, you will have Neville-Schwartz fluxes. And this is dual to some particular type of CFT, which is actually called a symmetric product orbifold CFT, or more precisely, some deformation, some marginal deformation thereof. So what is this symmetric product orbifold here? So sim n, oops. Nx. This is defined as taking n copies of the original CFTX and identify copies or befolding the copies by the permutation group. Okay. So what is n here? So n will depend on whether we have Ramon-Ramon and the Schwartz flux, and will be Q1, Q5, and Cx. So the central charge of the CFT will be 6 in the Ramon case, and in the Neville-Schwartz case, it will be Q1 and 6Q5, in such a way that the central charge, the total central charge of the dual CFT, in the large charge limit is given by 6q1, q5. So this is actually the counterpart of, so this is the counterpart of the more usual ADS-CFT statement that type 2B string theory on ADS5 process 5 is dual to SUN n equals to 4 super Young mills. And that is obtained in that case derived from a stack of D3 branes. One should actually mention that the duality in so usually in 3 dimensions, many things simplify. So we like to use 3-dimensional toy models because a lot of things, for example, pure gravity has no degrees of freedom, lots of things simplify. But in that case, one has to confess, I have to confess that the 3-dimensional version of ADS-CFT is weaker than the 5-dimensional version. And this is because both sides of the correspondence here actually have moduli. So they have 20 moduli. So on the left-hand side, the moduli are actually the shapes of the tori and the fluxes through the different parts of the space. And on the right-hand side, the moduli are actually marginal deformations of the symmetric product orbifold theory. So the point is that, yes.
Can I ask a question?
Yes.
So in the previous slide, how many times are these branes wrapped around T4?
How many times are the branes wrapped around T4?
And what is the parameter in the CFT which tells us, like, is there a parameter in the CFT which captures this aspect?
I'm not sure, actually. I am not sure. I had in mind that it was wrapped once around the T4.
I see.
I should check. So the thing with the parameters in the CFT are all these marginal operators that you have in the symmetric product orbifold, which are these twist 2 fields. So I'm not exactly sure that they are actually related to how the branes wrap T4.
I see.
But yeah. Okay, so I'm gonna say so no, the point is that identifying the precise, let me write up your question. Identifying the precise CFT dual is still an open question. And so I know there have been like many proposals, many debates, and I don't think there is a consensus yet as to identify what is. So the structure, the symmetric product orbifold structure, that's pretty well accepted. But what exactly are the details of the theory? For example, what exactly is X here? I think that's still open. So no, there is one observation that one can make. So the NS5F1 system is very interesting and actually stands out. Because string theory, because the resulting string theory on ADS3 is a target space of an exactly solvable world sheet theory. And this is thanks to the absence of Ramon-Ramon fluxes. And it's exactly solvable because string propagation on ADS3 with Neveu-Schwarz fluxes is actually the target space of an SL2R with the Witten model, where the level is given by the number of 5 grains. So here actually K is Q5, and it's given by the ADS radius over the strings of the string lengths. This is still R square of the ADS radius over alpha prime. So the SL2R Wieso-Minowitten model can actually be solved for finite values of K. So that's really nice because finite values of K means that we can solve string theory, we can solve the theory beyond alpha prime going to 0. We can solve the theory for finite K. So for finite alpha prime, which is solving classical string theory, while usually in ADS-CFT we're confined at the level of the supergravity limit where alpha prime goes to 0. Also in what follows, so the near horizon geometry in ADS3 CFT2 is ADS3 times S3 times T4, and I will mostly forget about the S3 times T4 factor. They will be there, I will just not mention them and see them as an internal CFT. Okay, good. So let me now try to review for some time, pretty quickly, strings on ADS3, because this is something that we will need later on in the talk when we will talk about the black string. So as we have mentioned, the SL2R, SL2R Wieso-Minowitten model describes strings on ADS3, and actually ADS3, the reason why this is the case is because ADS3 is actually the SL2R group manifold. So the same way that that the tree sphere is a group manifold of S3, ADS3 is the SL2R group manifold, and supported by Neveu-Schwarz fluxes. And the tree form here will just be the volume form in the group manifolds. So this model actually was solved in a series of 3 papers by Maldacena, Augury, and Son, was in one of the papers. Actually, the consistency of the model and the determination of the spectrum of the SL2R model, I mean, has been the subject of like a lot of works that started at the end of the 80s. And it was long thought that the SL2R Wieso-Minowitten model didn't make sense. So what was not consistent? Because of some, there were some conditions that to have a unitary model, you had to truncate the mass spectrum of the strings. So there have been a lot of papers starting at the end of the 80s to try to understand. So the SL2R model was really interesting because it was the first and maybe the simplest model to try to understand string theory in a curved space-time. So many papers, and then in 2000, Maldacena, Augury, and Son showed that, so Maldacena, Augury, and Son showed that the model is consistent. Plus, they determined its spectrum. So I want to review now for a second some properties of this Wieso-Minowitten model that would be useful later. So I'll start with the world sheet action and symmetries. So the action of the Wieso-Minowitten model is the following. So it's given by, so here we have the level. So that's a world sheet theory. It's given like this. G minus 1 d plus g. Minus 1 d minus g. Plus 2-dimensional Wieso-Minowitten term. So what are the things here? So here G is just an element parametrizing the SL2R group manifold that in the Maldacena Augury paper was taken as following. So I will denote by TA the SL2R generators. I will also be a bit sloppy between notations for the group and the algebra. SL2R are SL2, sorry, TAR SL2R generators, 2x2 traceless real matrices. So UV and rho are just coordinates on ADS3.
Sorry, last term in the action. K,
Yes.
gamma, what is it?
It's the West-Domino term in 2 dimensions. So it's a 3-dimensional integral over some manifold, and the boundary of that manifold will be the string world sheet. Okay, it's something like, it's some epsilon, well, so it's a 3-dimensional object that goes something like this. Sorry. I don't know if it's really clear. So G-1 dij, G-1 djj, G-1 dkg contract with an epsilon tensor. And that's a boundary term, actually.
2-dimensional.
So that's an object in 3 dimensions, but it's a boundary term, so it reduces to an integral over the 2-dimensional worksheet. So this is actually the volume form of ADS3. So the pullback of this on the 2-dimensional worksheet will give you the B field. So this piece here, that's just the killing metric that will give you the piece G mu nu D bar X mu D X nu. And this piece will give you B mu nu dx mu d bar x nu, if you will. So that will represent string propagation on the background with metric G mu nu. That will be just the killing metric on the group manifold, which is usually ADS3 metric, and with a B field whose field strength is the volume form on ADS3. Okay.
Thank you. Okay.
So so U, V, rho are coordinates on ADS3. So U, V are T plus minus phi, and X plus minus are coordinates on the world sheets. And so this describes string propagation on the killing metric of SL2R, which is given by these minus cos square rho pt squared plus 0 squared plus sin square rho d phi squared. And I will mostly know that G is SL2R. Okay, so what are the symmetries of this model? Well, the symmetries of this model are actually the affine symmetry G left hat times GR hat, where hat is the current algebra associated with the SL2R algebra. So the symmetry, so this affine symmetry is actually represented by the fact that the action is invariant under a shift of the G element by, to the left, something depending only on X plus, and to the right, something depending only on X minus. So that affine symmetry is actually generated by conserved and left and right moving currents. This is generated by GL. This is generated by GR. And one can see that these currents, the expression of the currents generating this affine symmetry, are just given by this expression. This is the left moving current, right moving current, given by this object here. And these currents are conserved. So D plus GL is 0, D minus GR is 0, and they are left and right moving. So GL depends only on X minus, and GR depends only on X plus. So, and yeah, so these objects are actually Lie algebra valued. So GL is a notation for GLA TA, and GR is a notation for GRA TA, and A is 1, 2, 3 for the 3 SL2R generators. No, we can expand these currents in modes. So GRA sum over N of GAN exponential INX plus GLA is this bar AN INX minus. Now, we know that, so the group element G was written exponential minus U over 2 T3, something exponential minus V over 2 T3. And G left and G right, so they generate this affine symmetry here. Okay, so now from this expression, the zero modes of GR, the zero modes will just generate constant shifts in U and V. So the zero modes of GA, of GR, will actually be related to the energy and the angular momentum, so to the charges of U and V associated with U and V, but U and V are related to T and phi. So the zero modes, G03 and G0 bar 3, will generate shifts of our U and V, and so will be related to the left and right moving energies of the string or to the energy and angular momentum of the string. So G03 and J0 bar 3 are related to generate shifts in time and shifts in the angular coordinates, so are related to the energy and angular momentum of the string through the following relations. E is just J03 is J0 bar 3, and L angular momentum J, sorry, is just J03 minus J0 bar 3. Some green. Okay, so the last thing, so this slide was a bit long, but it's over now. So the last thing that we need in this Weisel-Minowitten model is the stress tensor. So of course, this model, the Weisel-Minowitten model, is conformally invariant. So the stress tensor and Virasoro generators of this model can be related, are actually constructed out of these currents JL and J right. And so the stress tensor and Virasoro generators are given to, we have for the holomorphic component of the stress tensor is something like, so it's the product GR, and we have similar expression for T minus minus. And the Virasoro generators are also expressed as a quadratic combination of the currents modes. This is called the Sugawara construction. Okay. So the next thing that Maldacena and Augury studied, was the classical solutions, was to study classical solutions of the model. And actually looking at the equations of motion of the Weisel-Minowitten model just tells you that a solution, general solution just given by some part that depends, so some product, the product of a matrix that depends only on X plus, and another one that depends only on x minus. So they studied particular types of solutions. So these solutions here, they include time lag geodesics in ADS3. So these are given by an element G that would be some constant matrices U and V here, some parameter alpha here. And if you take a time lag generator of SL2R, so the coordinate, the time coordinate on the wall sheet, well, you will see that the corresponding solution will correspond to time lag geodesic in ADS3. Now you can just do the same thing, but instead of taking a time lag generator T3, you take a space lag generator, say T1. And what you will generate then is a space lag geodesic in ADS3. Okay, so then there is an interesting operation that Maldacena and Augury observed, pointed out, which is a spectral flow. That's an operation that we will need actually towards the end of the talk when we'll be interested in determining the spectrum of our theory. Spectral flow. If you give me some classical solution G, so for example, the time lag or space lag geodesic, well, you can generate a new solution from it by just multiplying to the left by something that depends only on x plus, and to the right by something that depends only on x minus. So that's still a solution. Where W, it's called the spectral flow parameter and is an integer. Has to be an integer to respect the periodicity of the world sheet. Now, if you change the G element, if you change G here, well, you will change the currents because the currents are expressed in terms of G. And so you will change the modes of the currents. So the effect of this operation on the modes, of the currents is as follows. So for the new solution, you will have this relation between the modes after and before deformation. And some extra thing here. Okay, so this transformation, you can show that it's an automorphism of the current algebra. So the GTL will still satisfy the same current algebra. And that operation will actually be used to determine the full quantum spectrum of the string. But no, the first thing we can see is, okay, what is the effect on time lag geodesics and space lag geodesic of this transformation? Well, the effect will be that the solution will acquire a sigma dependence. So sigma is a space coordinate on the wall sheet. So a spectral flow of time lag geodesics will generate strings that actually oscillate around the center of ADS3, and these are called short strings. These can be viewed as bound states, so they never escape to the boundary of ADS3. And the spectral flow of long strings, they correspond to strings that stretch from the boundary of ADS and eventually return there after having collapsed to a point. So short strings could be seen as bound states, and long strings could be seen as scattering states if we were on ADS3. Okay, so then what Maldacena and Augury did is that they determined the full quantum spectrum of the string. So here maybe, okay. So the spectrum of the quantum string is just given by the sum of products of representation of the current algebra. So our hat is just a representation of the current algebra of SL2R hat, and we need to tend to product them for the left and right sectors, and we have to sum over all the present other representations that are present. So representations of the current algebra, so they are built from a representation R of the zero modes, so just of SL2R, by acting on their states with raising operators, with the raising operators that are given by the modes of the currents. I'm just telling that they're annihilated by the positive modes, by the positive modes, yes. So you give me a representation of SL2R, you act with these current modes that will generate for you a representation of the current algebra. So what Baldassi and Augury showed is that the relevant, so the representation of theory of SL2R is slightly more complicated than that of SU2, for example, because the group is non-compact. So you have more representation. And what they showed is that the relevant representations of R are, so we have the principal discrete representation that will denote, they are characterized by their spin. It can be highest weight and lower weights, or lowest weights, and the states are, they share some similarities with the representations, the highest and lowest representations of SU2. But then we also have the continuous representation, denoted by, say, alpha j, where the states are given by, say, alpha m, so where m, so actually, so the eigenvalue of J0, if you diagonalize J03, the eigenvalue of J03, m, are actually not related to J, like it is for SU2. So m is alpha plus minus 1, minus 2, and actually we can restrict to alpha between 0 and 1. So alpha is a continuous parameter. And unitary representations are given for J that has this specific form, where S is real. So the corresponding representations of the current algebra built on these representations of SL2R by acting with these current modes here are denoted like this, with a hat. So what actually Baldassi and Augury showed, and that we had eluded other people that had tried to study the spectrum of strings on ADS3, is that to have a fully consistent theory, you need to build representations of the current algebra built from these GAN and J bar N modes. That's one thing. But that you also have to include the spectral flowed versions of these operators. So the definition of spectral flow is just this. So this is an automorphism of the algebra that preserves the algebra, but actually will generate new representations. So these new representations that are obtained by acting on the SL2R states with these guys instead of these guys, they will be they are denoted, and they are actually there for any value of W. They are written like so. So then what Baldassi and Augury did is that they determined the spectrum of strings in either of these representations. So these discrete representations are actually identified with the short strings, and the continuous representations are the quantum version of the long strings. So what they did is that they imposed the physical state condition, so on the spectrum. So careful that the physical state condition will also be shifted because of the spectral flow, because if the currents J are changed, then the Virasoro generators are changed too. So the condition L0 equals 1 will also be changed. And so they observed that strings, like short strings, they actually have a discrete spectrum, discrete energy spectrum, while long strings have a continuous energy spectrum. So with this spectrum of the SL2R Wess-Domino-Witten model, they show that the theory is unitary and that it is consistent. So there is no longer this bound, this upper bound on the massive string states. So, okay, I think I spent quite some time on that thing, but it's important because actually, so having the spectrum of strings on ADS3, this is actually a lamppost. This is what people use to identify what the dual CFT is. Because the dual CFT, well, should actually have the same, should reproduce that spectrum of strings on ADS3. So this result is important in that it constrains the nature and spectrum of the CFT dual to ADS3 string theory. And actually one proposal that has appeared recently, 2018, 2019, for dual to superstring theory on ADS3 times S3 is actually what proposed to identify what the seed theory here, what the seed theory appearing in the symmetric product orbifold was. And it was argued that this theory here, so the symmetric product of the seed theory that is n equals to 4 uval theory is a given central charge tensor with 4 free bosons and 4 free fermions, that this symmetric product reproduced the string spectrum on ADS3. Okay, so of course, at the beginning of the talk, I argued that I wanted to study non-asymptotically ADS spaces, and here I seem to have spent a lot of time just on ADS3. So indeed, what we have done here is that we have covered this central zone here. I have reviewed what we read in ADS3 CFT2 to to describe what we will need later to go away from ADS3, because now remember, we want to describe the black string, and the black string is not asymptotically ADS3. So what we want to do now is use this tool to try to see how can we go away from ADS3. So how can we go from describing a black hole that is asymptotically ADS3 to a black hole that is asymptotically flat? So we have seen that the SL2R Wess-Domino-Witten model describes strings on an ADS3 background. So one question we can ask is, how can we describe more general background? Well, an interesting observation that is due to these people here is that Wess-Domino-Witten models admit exactly integrable marginal deformations. So remember that an exact string theory background. Oh, yes, there's a question. Is there, no, just a camera. Okay, so remember that an exact string theory background corresponds to an exact worldsheet two-dimensional conformal field theory. So for example, the SL2R Wess-Domino-Witten model is a 2D CFT that corresponds to string propagation on ADS3. But no, Wess-Domino-Witten models, they admit integrable marginal deformations. What does this mean? It means that you can start with a Wess-Domino-Witten model and then deform it by adding to the action an exactly marginal operator. So of course, this operator has to be 1,1 by dimensional analysis. So this defines for you a new worldsheet theory that depends on this parameter lambda. So Wess-Domino-Witten models, they have natural 1,1 operators. For example, the operator J1, J bar 1, well, that's a marginal operator. So the currents, they are holomorphic and anti-holomorphic. J1 is 1,0 and J bar. So this is 1,0 and this is 0,1. So this is a potential marginal operator, and no one has to be sure that it's exactly marginal. By exactly marginal, I mean that once you go away a finite distance from this Wess-Zumino-Witten model, well, the theory retains 1,1 operators. But actually, you can show that this operator in particular is exactly marginal. So you can start with the Wess-Zumino-Witten model describing strings on ADS tree, and you do marginal deformation. You get a new conformal field theory that describes string propagation on a new background. So now the observation is that the black string solution that we are interested in can be obtained from the SL2R Wess-Zumino-Witten model by a marginal deformation and by precisely a J1, J-bar1 marginal deformation. So what do? We start with the Wess-Zumino-Witten model on SL2R, and we parameterize the group element slightly differently than in Maldacena augury. So G is an SL2R group element, and then the killing metric corresponding to G, will actually be a BTZ black hole. So if I compute trace of G minus G dG, J minus G dG, corresponding to this element G here that has coordinates U, V, and R, the metric, this would correspond to string propagation on a metric, oops. That is given by this. This plus some extra B fields and a constant dilaton. No, so this is a starting Wess-Zumino-Witten model. We turn on a marginal operator that is given by the product of J1 and J-bar1. So remember, J1 and J-bar1 are actually the generators of left and right translation by a constant element. So they correspond to constant shifts in U and in V. So they are actually related to the Noether currents associated with the target space, the target space action. They are not quite exactly the same. For this talk, we'll just ignore the difference between the two. No, once you do, yes.
What metric is this?
Sorry?
What is this metric? Like, what did it do?
So this metric here, that's the BTZ black hole.
I see. Okay. Okay.
The horizons are just here. It's R squared is TU squared TV squared. And so this is just a rewriting of the BTZ metric where UV are related to T and phi, the usual ADS3 coordinates, and R has been redefined.
Okay. Okay.
So this describes string theory on a BTZ black hole background. We turn on the deformation, and of course, once we turn on the deformation, the background will change. So for one thing, the deformed action will actually now satisfy the following relation. So by construction, the deformed action will satisfy this relation. Okay, so there are various techniques actually to read what the background is after the deformation, and the result is that the background fields correspond now to string propagation on this metric. So when lambda is 0, of course, we cover BTZ, but when lambda is non-zero, when we turn on the deformation, we get this metric here. Now we can do a change of radial coordinates. So this metric is a bit messy, doesn't tell us much, but we can do a change of radial coordinates in this metric and observe that when the deformation parameter takes some specific value, the metric takes this form. Okay, so now let's go back to one of my first slides. And let's go back to the Horne-Horowitz metric. And compare it to the metric that we just obtained. That's we actually observed that when j equals 0, so this metric that we have has 3 parameters, j, m, and q. It corresponds to a rotating object. When j equals 0, this metric is exactly the Horne-Horowitz metric. Okay, so what we have found in doing this JJ bar deformation of the BTZ black hole, world sheet theory, is actually a rotating generalization of the Horne-Horowitz black string. There's also one observation we can make that we will need, is that the deformed background that we have here, we can obtain it as a sequel, as a series of transformations that are called TST transformation. So the original background here has 2 commuting isometries, du and dv, that are actually associated with dt and d phi. So time translation invariance and axis symmetry. So when you have a background that has 2 commuting isometries, you can apply to that background what is called a TST transformation, which means that you do a T duality along one direction, you shift the other direction by this u dependent quantity here, and then you do a T duality along the u direction once more. And if you do this TST transformation on the BTZ background, well, the background you get is that of the rotating Horne-Horowitz black string. Okay, so here where do we stand? So now we can take stock. So what do we have? So in the underformed case, at the classical supergravity level, we have ADS3 and BTZ. That we have seen is described, that it's described at the level of the world sheet. So it's at the level of string theory. It's an exact world sheet theory that is captured by the SL2R Reissner-Nordstrom model. And we have also discussed that the dual theory of ADS3 has to be some 2-dimensional CFT, even though we cannot identify it in full precision unambiguously. So then what we have observed is that if we do a TST transformation on ADS3 on the ADS3 background, well, do a TST on the supergravity background, what we get is just a 3-dimensional black string, the solution that we are interested in since the beginning. And we have seen that this actually corresponded at the level of the world sheet, that corresponded to a marginal deformation. And the background was here, was a Reissner-Nordstrom action plus a marginal deformation by this bilinear of currents J1 and J1 bar currents. So now the question we can ask, is, well, what is here? What is here? So that question, so back in the days when I was doing my PhD, I was sort of studying these marginal deformations of Reissner-Nordstrom models and getting all these nice backgrounds that looked asymptotically flat, or at least that had a different asymptotics than ADS3. And I remember that asking the question, so okay, what is there? What should fill the question mark is one of these questions that I had in the back of my mind for quite some time. One of the things that you put in postdoc applications, but you don't really know where to start and how to tackle that question. And even worse, actually, when I was talking to maybe more senior scientists about that project that I had. So what should fill in? What should go at the place of this question mark? What you would always get is there's a statement that since the marginal deformation or this TST changes the asymptotics, that should correspond to a UV modification of your theory. So that should correspond maybe to a deformation of your CFT, but that would be an irrelevant deformation. And well, irrelevant deformations, they are kind of scary, because usually to compute physical quantities, you need an infinite number of counter terms. So the theory is highly ambiguous when you start to doing irrelevant deformations. So back then, every time I was talking about this with people, I mean, I got a bit discouraged that studying irrelevant deformations of a CFT to understand the dual of the black string should be too hard of a task. But actually, maybe you know there is this quote. I don't exactly remember what the quote is, but so the quote is that when a senior scientist tells you that something can be done, he's most likely to be right. But when a senior scientist tells you that something cannot be done, he's most likely to be wrong. And actually, I should have sort of like more take this quote as mine and try still to do something about irrelevant deformations. But I didn't. And so some time passed and I had that thing in the back of my mind. But then something happened. So before something happened, so this is the full plan I had put at the beginning. So this is the ADH3 sector. This is what we have reviewed: marginal deformations and TST, and this is the question mark that we'll try to uncover. So actually, many years later, in 2016, people started to study certain TTbar, certain irrelevant deformations of two-dimensional field theories. So these deformations, so the TTbar deformation is actually an irrelevant deformation of 2D quantum field theories that are triggered by some operator, some irrelevant operator that is defined like this. It's given by the determinant of the stress tensor. So the corresponding action of this, the deformed theory, so mu is a deformation parameter, will just satisfy by definition this thing, dxx, dx bar x bar, minus dxx bar, dx bar x. So this is just the determinant of t. So x and x bar are coordinates of the QFT2. And this can still be written as, this can also be written as in terms of these noether currents that repackage the stress tensor. So this is just a definition of J1 and J2 bar. The indices doesn't matter, just some convention. So J1 and J2 bar just is a way to repackage the stress tensor in terms of space-time one forms. And what is remarkable is that even though the deformation is irrelevant, many physically interesting quantities can be computed exactly and explicitly in terms of the undeformed theory. So let me state two results that occur from this theory. For example, the finite volume spectrum can be computed. So the energy and angular momentum and the deformed theory by an amount mu on a cylinder of radius r can be expressed in terms of the undeformed energies and angular momentum by this expression here. So that just depends on the radius of the cylinder, undeformed energies, and the deformation parameter. So angular momentum is not changed because it's quantized. So if the QFT is a 2D CFT, well, we are customary to use the modes, the left and right moving energies, which are the zero modes of the Virasoro generators. So in terms of the left and right energies, this modified spectrum can be expressed like this. It's undeformed energy, deformed energies.
Excuse me, I have a naive question.
Yes.
So T here was the stress tensor for the undeformed CFT, right?
What is T? Sorry.
Not on this slide, on the previous slide when you did the deformation, right? T stress tensor.
Oh yeah. So T is the stress tensor of the undeformed theory, but then, of course when you go away a finite amount of mu, T becomes a stress tensor of the deformed theory again.
So that's why you.
So there should be a mu dependency.
Oh, that's why you have T Z Z bar components there.
Exactly.
Okay.
Yes.
Okay. All right.
That's one reason. And you could also ask, why do I have X bar and X bar X? You know, because if the system is rotationally invariant, why should you have? Well, you allow yourself to work maybe with a stress tensor that is not in Bell-infinity form, that's not identically symmetric, if you know. But yeah, so that thing varies along the flow.
Okay, thank you.
So the finite volume spectrum can be obtained, but also if the TTbar deformation is that of a two-dimensional CFT, you can also express the entropy microcanonical ensemble. So count the asymptotic growth of states. So there is some regime in which the asymptotic growth of states can be counted a little bit like the Cardi formula, where, so this is a number of states that have, so the entropy of the number of states that have energy E left and E right, and this will depend on the seed of the undeformed CFT, again on the radius and on the deformation parameter mu. So this leads us to the proposal. So the proposal that we made is the following. So we claimed that string theory on a TST transformation of ADS3 times some n-terminal factor with Nevers-Schwarz fluxes is actually dual to a TTbar deformation of the original CFT that was dual to ADS3. To be more precise, it's what is called a single trace deformation of the TTbar deformation, a single trace version of the TTbar deformation. I will explain in a minute what I mean by this. So this is the proposal that we made. So I need to mention that there are related proposals that were made by various authors. And actually the deformation they considered was actually slightly different. The deformation they considered was actually a null deformation of ADS3, while we have considered a space-like deformation of ADS3. Actually, I think I gathered that Sumansu Chakraborty will be your speaker next week, and he might be talking about these topics here, about their approach. So what we did is, no, okay, what do we mean? What did we mean by single trace TTbar deformation? No, assume. Remember that the problem is that we don't really know what the original CFT is, but we will only assume that the original CFT2 has the generic structure of a symmetric product orbifold. That is a symmetric product orbifold of a seed CFT with central charge 6K, where K is the number of 5 branes generating the background, and P is the number of F1 strings. So we have CX 6K, C 6KP, with P Q1 is a number of F1s generating the background, and K is a number of F5s, NS5 generating the background. So what did we mean by single trace? The single trace deformation is defined by the following equation. That would be the sum over all copies of GI1 add to bar. So remember that so GI is the one form that packages the stress tensor node of each copy. So this is the single trace deformation. So we take each copy, do a TTbar deformation of it, and do the symmetric product. Okay, so what are the evidences for this proposal? So the first evidence comes from the thermodynamics. So the total entropy of our symmetric product, so assuming the structure that we have, so the total microcanonical entropy of this theory is given by this formula here. So the number of states with energy E left and E right is given by this formula that involves, so P is a number appearing in the symmetric product, R is the radius on which the theory is compactified, we have E left and E right, left moving and right moving energies, and we have the central charge, the seed central charge. So now let's compare this to the Bekenstein-Hawking entropy of the black string. So the black string, so remember, the black string has conserved charges. The black string has a conserved charge, a left conserved charge associated with scaling vector QU. So the expression is something like this. The expression is not important, but so that you see a little bit how it looks like. Remember, the black string dependent on T1, TV. And so we have something like this for the charges. This can be computed by standard methods. So we have a left and a right central charge. So and left and right charges, so that are related to the mass and to the angular momentum of the black string. Then we have an electric charge that is given by P, the number of Q1 generating the original background. And we have a magnetic charge that is given by the level of the corresponding of the original Wisdom-Witten model. So notice that these quantities here are unchanged under the deformation. Now we can also compute, well, simply the Bekenstein-Hawking of the black string, just given by the area of the horizon. What we find is the following. So the expression of the Bekenstein-Hawking entropy expressed in terms of the charges, this can be computed from scratch. This. No, of course, it's natural to identify the gravitational charges Q left and Q right with the left moving and right moving energies of the dual theory. Also, we know that the central charge of the dual theory of the dual seed theory before the deformation was given by 6 Kp, which is just 6 QE/QM. Now, if we compare this expression with this expression, we see that there is a complete agreement. There's a complete match. At the condition that the deformation parameter, so that the deformation, the TST parameter lambda on the gravity side is related to the deformation parameter in the field theory by this expression. So this tells us that the Bekenstein-Hawking entropy of the black string can be matched to the entropy of a thermal state in a TTbar, single tier TTbar deformed theory. Okay, so now there is another evidence, but I realize it's already late. I can wrap in 1 minute or in 5 minutes. I don't know if I realized that I was a bit slow. So okay, but let me take this. So the second evidence is the following. So in the ADS3 case, I showed that we could solve the solve the string spectrum of strings propagating on the ADS3. No, it's actually possible to go even further. It's possible to also determine the string spectrum on the TST transformed background. So this is a result due to Aldai, Arutyunov, and Frolov, that so the equations of motions and Virasoro constraints of a TST transformed theory can be obtained from those of the original theory that we know by a non-local change of coordinates. So remember that our TST was to do a T-duality along U, a shift of the V coordinate, the other V coordinate, and again, a T-duality along U. Well, in that case, the non-local change of coordinate that you need to do looks something like here. I'm not exactly really precise, but we need to define new coordinates. So now we have our TST transform backgrounds that has, so our TST transform backgrounds has coordinates U, V, and R. And I define new coordinates, U hat, V hat, and R hat, such that dV hat is related to dV by this quantity here. And similarly for d bar U hat is something like this. So I'm shifting dV by this quantity here. So remember J1 was the current that was associated with translations in U. Okay. Then the observation of this paper here is that the background J hat, in terms of these hatted coordinates G, B, and phi, the background is exactly the same, becomes exactly the same as that of the undeformed background, which is just the background of a string moving on ADS3 or on BTZ. But with non-local boundary conditions on U hats and V hats. So what are these non-local boundary conditions? It's just that U hat of sigma plus 2 pi at the end of the wall sheet is U hat of sigma plus 2 pi times some quantity. What is this quantity? Well, this quantity will be the winding for a string winding a couple of times around the string around ADS3. So that would be the case for the undeformed model, just capturing the float sectors. But then in the deformed case, the non-locality comes from this term here. You have the integral with you have this lambda. If lambda is 0, this term is not there. When the theory is deformed, we have this term, and that's given by the integral of the J1 current over the wall sheet. But as we have seen, this is just the zero mode of J01. And J01 was just the right energy because J01 just generates shifts in one of the coordinates in U or in V, and J0 bar 1 will generate translations in U, and that would be E left. Now these twisted boundary conditions, they can actually be implemented by related the form, so the non-local coordinates to the undeformed local coordinates by this quantity here. Now remember that if you change the coordinates, you change the group element. But if you change the group element, you will change the current that is built out of this. And that's you can observe that the current associated with these non-local coordinates for the deformed theory are related by the currents in the undeformed theory by a spectral flow operation. And the spectral flow here will depend on gamma U, and this gamma U depends on the left and right energies. Now, if the currents are changed, Well, the Virasoro generators are built as quadratic combinations of the current. So the Virasoro generators will also change. And now we can express the Virasoro generators of the deformed theory, the L0 hat here, in terms of the generators of the undeformed theory, the tildes. Now, to get the physical spectrum, we just need to impose a physical state condition, L0 hat equals 0. And if we impose that condition, we along the whole deformation line, so L0 hat of lambda equals 1 equals L0 hat of 0 equals 1, then we will be able to extract from this physical state condition the energies E left of lambda and E right of lambda and the deformed strings for the deformed string spectrum. And this is the result that we are getting. So this is the result for the left and right moving energies in the string spectrum after the deformation, E left and E right of lambda, and before the deformation, E left and right of 0. But wait, let's now go back at the energy spectrum in the TTbar deformed theory. That's what this thing here. Oops. And let's compare this to the spectrum of strings that we got. Well, the spectrum of strings on the TST transformation is exactly matched to the spectrum of a TTbar deformation if we make the following identifications. L is R times omega, and lambda is related to mu k over R squared. But lambda is mu k over R squared. That was exactly the relation that we needed between the gravity and field theory parameters for the entropy to match to. So why is this interesting here? What is the observation here? Thus, what we have. So we started with a spectrum of strings on ADS3. So given by E and G. This is the discussion that we made with the Malassina and Augury paper. Of course, the point is that this should match spectrum of the dual CFT. This dual CFT, we don't quite know it so far. On the other hand, here we did a TST transformation, and we got the spectrum of strings on TST transformed ADS3. And we got a spectrum E of lambda, J of lambda. So the dual theory to that string background, well, should have the same spectrum. But what we have showed is that the relation between E lambda and J lambda and EJ is precisely that between a CFT and its TTbar deformation. So this should suggest that what should go here is indeed TTbar. And this is true even if we don't really know the precise nature of the theories here on the right-hand side. Okay, so the original question was to start from this point here and to walk through this diagram and answer the question and ask the question of what should we put here in place of the question mark. And we have actually provided evidence that what should replace the question mark as the dual theory to the three-dimensional black string and corresponding to a marginal deformation of an SL2R Reissner-Nordstrom model should actually be a single trace deformation of a 2D CFT. So I had a couple of further discussion, but maybe I'll leave this to later. And thank you very much for your attention.
Thanks, Stephane, for that wonderful talk. Now, if people have any questions for the speaker, you can ask now.
I have a question. Could you, so what other tests could you suggest to check how far it is really true?
Right. So see, this wasn't, so what we have checked here actually is one thing. So how does it work for BTZ? How did things work for BTZ? Things work for BTZ in the following way. So BTZ belongs to a phase space that has conformal symmetry. And the entropy of BTZ is reproduced by a Cardi formula. So these are two indications that there should be a CFT dual to a gravity theory that has black holes and in ADS3. So here in the TTbar case, one thing that we did is to match the thermal entropy of the black string, well, the Bacon-Hawking entropy of the black string with a thermal entropy in a TTbar deformed CFT. So one thing we don't really have here is a phase space. What is the gravitational phase space of a theory that would include the black string, and what are its symmetries? This is one thing we don't really know. So for example, what is the counterpart of Horne and Horowitz for the black string? What are the symmetries? So at some point we try to do this thing, but it's not really clear what the gravitational phase space is and what the symmetries should be. So that's one question. So what is, or put it in a different way, what is the TST transform of Horne and Horowitz boundary conditions? That's one thing. So another thing is that we have matched the thermal entropy of the black string with the thermal entropy of a TTbar deformed CFTs. Of course, we know that there are many other observables that we can compute holographically. For example, another one is entanglement entropy. So people computed the expression of entanglement entropy in TTbar deformed CFTs. So that's the field theory side, and I think the field theory side already is known. Now the question, we know how to compute in principle, at least in ADS spaces, we know how to compute entanglement entropy holographically, given by the lengths of geodesics that are hanged at the boundary. So for example, in ADS CFT, the length of the geodesic will be just the entanglement entropy of the interval on which the geodesic is hanging from. I don't know of the counterpart of this for the black string. So for example, is it possible to compute entanglement entropy by a geodesic length computation in the black string and then comparing it to the expression of entanglement entropy in TTbar deformed CFTs? This I gather should be doable if the duality is true. Another thing, for example, something else that we can do in BTZ black holes is compute quasi-normal modes. So for the BTZ black hole, the locations of the quasi-normal modes in a BTZ black hole background, they match the poles of the thermal correlation functions in the dual CFT. So thermal correlation functions in the TTbar deformed CFTs should be known. So the question is there a match between the quasi-normal modes of the black string and these poles? Yeah, what else did I put? Yeah, extreme. Yeah, usually there's much to learn about, like looking at extremal solutions, and especially even recently, we discovered that there are things that we didn't quite appreciate in extremal BTZ black holes. For example, if you take an extremal BTZ black hole, you can observe that excitations above extremality are governed by Schwarzschild theory. Actually, it's governed by the Schwarzschild sector of the CFT dual to BTZ. There are some papers by Gosh, Toriachi, and Maxfield doing this. No, there is a funny thing about the extremal black string. So the extremal black string has an near horizon geometry that is ADS. It's actually the same as extremal BTZ. So you can ask the question, well, is there a Schwarzschild sector that survives even in a TTbar deformed CFT? And yeah, so I think these are a couple of things that should or could be done to, well, just to go a little bit further the matching of thermal entropy, which is of course the level 1 evidence that you would have.
All right, thank you very much.
Any more questions? Okay, if not, let's thank Stephane once again. And we'll see you guys next time.
Thanks very much.
Stephane.
Thanks very much. Bye-bye.
Bye.